All right, people, what's up? I'm going to show you a short, quick video on sigma and pi bonds. Today we're talking about intramolecular bonds, and this intra means bonds that are within, I don't know if I spelled that right, the molecule, okay? Or if I phrased that right, but what I mean is the bonds that are within. We're not talking about bonds that hold two different molecules together. We're talking about bonds that hold atoms together that are inside of a molecule, okay? So there's two types of these bonds. There's sigma and pi bonds. And sigma bonds are the first or the initial bond that occurs between the two atoms. And the pi bonds are the second and third bonds. We use the pi to represent them, okay? Now, the difference between the sigma and pi bonds is pretty subtle, but we label them differently. And let's take a look here. Let's think about, I don't know, nitrogen. If we have a nitrogen molecule, nitrogen, you know, is N2, right? It's one of the deadly seven. So a nitrogen molecule would have how many bonds? Yep, it'd have 3 bonds. It'd be triple bonded, okay? So right here, this is a nice Lewis structure of nitrogen. And let's talk about that Lewis structure real quick. We have a nitrogen here and another nitrogen here. And we think about what this electron's doing. We'll have 2 electrons, okay, that are going to be shared between this nitrogen on this axis, this primary axis, okay? So these 2 electrons that are being shared like this, I'm just drawing it as a figure 8. This is a sigma bond. Now, if we have orbitals that go up like this, and this isn't necessarily a px or a py, okay? It's kind of like that, but a little bit different. But we have orbitals that go up like this, and then they overlap here on this other axis. These, where they overlap here, where these atomic orbitals overlap, you have a sharing that occurs right here and right here. So these are the pi bonds. And I know you're like, this is some weird stuff. Well, anyway, this right here, this picture is represented by that. See, this is that is that, and this is that. Does that make sense? And we'd have 2 other electrons that aren't doing anything. If we go back to the original picture, I said this is a good Lewis structure of the molecule. Well, it's not quite done. For it to be a perfect Lewis structure, you would label a sigma and a pi and a pi. So let's draw something bigger. Let's draw something bigger. How about we draw, and I'm done drawing this, okay? Let's draw like, how about CO2? We know that CO2 looks like this. So this carbon's happy. It's got 1, 2, 3, 4, 5, 6, 7, 8. And this oxygen would have 2 unpaired bonds, 1, 2, 3, 4, 5, 6, 7, 8. Now, if I'm going too fast, you need to watch the other videos, okay? So we know oxygen's going to have 2 lines attached to it, and carbon's going to have 4. That's from the first video on this, so if you don't know this, you need to go back and take a look at it. All right, whoops, I made a little squiggle there. All right, now here's how we can, let's pretend that's not there. Did not mean to. There we go. All right, that's just a goof up. All right, so we know what this carbon dioxide molecule is. Now, if we're going to label it, we put a sigma on the first line, and you put a pi on the second one. Mr. Perkins, does it matter if the sigma's on top or the pi's on the bottom? No, nobody cares. Okay? Now, this one's done. Okay? Now, we could think about it. We could talk more about it. It's linear and it's nonpolar, right? Those are other things we know about it. How about I draw you something like, if we drew like a tetrahedral molecule of methane. And now we don't need to put anything else on here because all the H's are already happy and the carbon's happy. There's no unbound pairs. I could say, hey, you need to label this. Well, again, just like in the other videos, the sigma is the first one you put on there. So the first bond between carbon and hydrogen is sigma. So all of these are sigmas. Does that make sense? And if it doesn't, I want to draw one more that should make it perfectly clear. What if we did like hydrocyanic acid, or got a hydrogen, carbon, and a nitrogen? Okay. Now start thinking about what this should look like. All right. You know the carbon's going to have 4 total, right? And you know the nitrogen's going to have 3 lines total, and you know the hydrogen is going to have 1. So if you did this, this one's almost done. That's right. Bam, bam. Now it's done. Then you can label. What's the first bond here? Sigma. We can say, what's the first bond here? Sigma. And you could put it in the middle, really, but it doesn't matter. Sigma, and then now the ones that are left over, those are the secondary bonds, or the pi bonds. So you can see every time I drew a second or a third bond, I put the pi symbol on it, okay? Every time I drew an initial bond or the first bond, I just put the sigma symbol on it, and that's it. Now, this is going to get harder tomorrow when we do hybridization. And why do we do this? Because if you have a nitrogen molecule, it's really bonding in these 3 different places. Now I'm going to give you a couple to practice, and I hope you made it through this video. And now that you've watched the video, here's your homework. I'm going to ask you to draw these molecules as completely as possible. And then I'm going to give you a blank worksheet to put them on or to turn in. So number 1 is water. Draw and label this completely with all the unbound pairs and label each bond as sigma or pi. Number 2 is chlorine. Label everything, put your unbound pairs on there, label the bond as sigma or pi. Number 3 is S2. So label the bonds as sigma or pi and put all your unbound pairs on there. Number 4 is pH3. So build that molecule, label it, put all your unbound pairs on there. And then number 5 is HSIP, hydrogen, silicon, and phosphorus. And yeah, they're in order, so it'll be easy to do and label all the unbound pairs, etc. Good luck. Also, I want you to do this. Don't give up. When you do each one of these, for each picture, for each structure that you draw, make sure you also label what shape you think it would take and whether it's polar or nonpolar. All right, there we go.